What if you could lose 23 years in an hour? Not lose them to sleep or distraction or boredom. Actually lose them. Experience 60 minutes while the rest of the universe experiences 2 decades. Interstellar showed us this nightmare. Miller's planet. Cooper descends, collects samples, barely escapes. 1 hour and 14 minutes on the surface. 23 years pass for everyone else. But here's what makes it truly haunting. It's not fiction. The physics behind that scene is real. Kip Thorne, the Nobel Prize-winning physicist who consulted on the film, didn't invent the time dilation on Miller's planet. He calculated it using Einstein's equations. He showed Christopher Nolan that, yes, if you orbit close enough to a rapidly spinning supermassive black hole, time genuinely slows down that dramatically. 1 hour can equal 7 years, not in a screenplay, in reality. Time, the one thing we all assumed was absolute, universal, unchanging, is actually flexible, malleable, bendable. Gravity warps time. Speed warps time. Right now, as you sit watching this video, astronauts orbiting Earth are aging slower than you are. GPS satellites are ticking faster than clocks on the ground. Particles raining down from space are living longer than they should. Your head is aging faster than your feet. Time is not what you think it is. And we've proven it. With atomic clocks, with satellites, with particle accelerators, with astronauts, with mathematics so precise and experiments so careful that there's no doubt left. Time dilation is real. Welcome to the science of time dilation. I'm going to show you why Interstellar's most heartbreaking scene is grounded in one of the most profound discoveries in human history. We're going to explore how gravity bends time, how speed slows time, how you can travel to the future by moving fast enough or getting close enough to massive objects. And before we dive deep into breaking time itself, hit that like button and subscribe to Whispering Wonders of Science. Because understanding how a black hole can steal decades while you experience minutes, that's exactly the kind of mind-bending reality we explore here. By the end of this journey, you'll understand the physics that broke Cooper's heart. You'll understand why time is relative, and you'll never look at a clock the same way again. Ready? Let's break time. For thousands of years, for basically all of human history until 1905, we believed something that seemed self-evidently true. Time flows at the same rate for everyone, everywhere, always. A second for you is a second for me. An hour here equals an hour there. Whether you're sitting still or running at full sprint, whether you're at the top of Mount Everest or at the bottom of the Mariana Trench, whether you're on Earth or Mars or floating in the depths of intergalactic space, time marches forward at exactly the same unchanging pace. This belief made perfect sense. It matched our everyday experience. When you and I agree to meet for coffee at 3 p.m., we both know what that means. When we synchronize our watches, they stay synchronized. When we observe the universe, everything seems to happen according to a universal timeline. Isaac Newton, one of history's greatest scientific minds, formalized this intuition. In his Principia Mathematica, published in 1687, Newton described what he called absolute, true, and mathematical time, which of itself and from its own nature flows equably without relation to anything external. In Newton's universe, time was the stage upon which all events occurred. The stage existed independently of the actors. It didn't matter what happened on the stage. Time itself remained unchanged, flowing uniformly from past to future, the same for all observers. This wasn't just Newton's opinion. This was the foundation of classical physics. Every equation, every prediction, every calculation assumed a universal time that coordinated all events across the universe, and it worked beautifully. Newton's physics predicted planetary motions, explained tides, allowed us to build bridges and steam engines and send men to the moon. We had no reason to doubt it. And honestly, in everyday life, Newton was right. For speeds we normally experience, walking, driving, even flying in jet airplanes, and for gravitational fields we normally encounter, standing on Earth's surface, climbing mountains, descending into caves, time does flow at essentially the same rate for everyone. The differences are so microscopically small that you need atomic clocks accurate to billionths of a second to detect them. But here's the thing about physics. The universe doesn't care about human intuitions. The universe doesn't care that time seems absolute. It doesn't care that our everyday experience suggests time is universal. The universe operates according to its own rules, and those rules, it turns out, are far stranger than Newton ever imagined. The first crack in the foundation appeared in the late 1800s. Physicists studying light and electromagnetism kept getting results that didn't quite fit with Newton's absolute time. James Clerk Maxwell's equations describing electromagnetic waves, light, radio waves, X-rays, seemed to suggest something weird about the speed of light. Then came the Michelson-Morley experiment in 1887. Physicists Albert Michelson and Edward Morley tried to measure Earth's motion through the luminiferous ether, a hypothetical medium that was supposed to carry light waves the way air carries sound waves. They expected to find that light traveled at different speeds in different directions, depending on Earth's motion through the ether, like how sound seems to travel faster downwind and slower upwind. But they found nothing. Light traveled at exactly the same speed in all directions, regardless of Earth's motion. The experiment was repeated many times with increasingly precise instruments. Same result. This was deeply puzzling. How could light always travel at the same speed, regardless of how the observer was moving? Scientists proposed increasingly elaborate explanations. Maybe the ether was dragged along with Earth. Maybe measuring instruments contracted in the direction of motion. Maybe. But one young physicist looked at the evidence and came to a radical conclusion. Maybe there is no ether. Maybe light doesn't need a medium. Maybe the speed of light is simply constant for all observers, regardless of motion. And maybe, just maybe, this meant that time itself wasn't constant. His name was Albert Einstein, and he was about to turn physics upside down. The year is 1905. Albert Einstein is 26 years old, working as a patent clerk in Bern, Switzerland. He couldn't get an academic position after finishing his doctorate, so he spends his days evaluating patent applications for electromagnetic devices. But in his spare time, during lunch breaks, in the evenings, on weekends, he's thinking about light, about motion, about the strange results of the Michelson-Morley experiment, about Maxwell's equations. And he has an idea, a simple idea, an idea so radical that it will completely transform our understanding of space, time, and reality itself. What if the speed of light is always constant? Not approximately constant, not constant under certain conditions, but absolutely, fundamentally, invariably constant for all observers, regardless of their motion. This one assumption, this one postulate, has extraordinary consequences. Think about it. You're on a train moving at 100 kilometers per hour. You throw a ball forward at 50 kilometers per hour relative to the train. To someone standing beside the tracks, that ball is moving at 150 kilometers per hour. The speeds add. That's common sense. Now replace the ball with a beam of light. You're on a spacecraft moving at half the speed of light. You shine a flashlight forward. Common sense says the light should be traveling at 1.5 times the speed of light relative to a stationary observer, but it doesn't. According to Einstein, it travels at exactly the speed of light, the same speed it would travel if you were standing still. 299,792.458 kilometers per second. No more, no less. How is this possible? The only way to make this work, the only way the mathematics can balance, is if time itself adjusts. Time must flow at different rates for different observers. Time must slow down for moving observers relative to stationary ones. Einstein published this idea in a paper titled On the Electrodynamics of Moving Bodies in 1905. Today we call it special relativity. The core insight is breathtaking in its simplicity. The laws of physics are the same in all inertial reference frames, and the speed of light in vacuum is constant for all observers. From these two postulates, everything else follows. Time dilation, length contraction, the relativity of simultaneity, mass-energy equivalence, E equals mc squared. Einstein derived all of this without conducting a single experiment. He did it through pure thought, working out the logical consequences of his postulates using mathematics and imagination. And here's the stunning part. He was right. Every prediction special relativity made has been tested and confirmed. Time dilation has been measured in particle accelerators, in atomic clocks flown on airplanes, in GPS satellites, in cosmic ray particles raining down through our atmosphere. Every test confirms Einstein's theory to extraordinary precision. Time is not absolute. Time is not universal. Time is relative. The rate at which time flows depends on how fast you're moving relative to an observer. The faster you move, the slower your time ticks from the perspective of someone watching you. This isn't an optical illusion. This isn't a measurement error. This isn't a quirk of clocks or instruments. Time genuinely flows at different rates. A moving clock literally, physically, actually ticks slower than a stationary clock. A person traveling at high speed literally, physically, actually ages slower than a person at rest. Einstein didn't stop there. 10 years later, in 1915, he extended his theory to include gravity. General relativity revealed that massive objects don't just curve space, they curve time as well. Gravity slows the flow of time. The stronger the gravitational field, the slower time ticks. This means time flows slower on Earth's surface than in orbit, slower in a valley than on a mountain, slower near a massive star than in empty space, and near a black hole, time can slow to a crawl. Einstein's theories, special and general relativity, are now the foundation of modern physics. They explain phenomena from GPS satellites to gravitational waves, from particle physics to cosmology. And they all stem from one simple radical idea. The speed of light is constant. From that seed grew a revolution in our understanding of time itself. Let me introduce you to Alice and Bob. They're twins, identical, born on the same day, same hour, same minute. They've aged identically their entire lives. Today, they're both exactly 30 years old. But today, their paths diverge. Bob boards a spacecraft. This spacecraft is special. It can accelerate to a substantial fraction of the speed of light. Bob's mission? Travel to a distant star system and return with data about potentially habitable planets. Alice stays on Earth. She'll continue her life here, working, raising a family, growing older. The spacecraft accelerates. Bob feels the acceleration push him back into his seat. Over weeks and months, the engines fire continuously, pushing the craft faster and faster. Eventually, Bob reaches a cruising speed of 90% the speed of light. At AOT, this incredible velocity, Bob travels toward his destination. Years pass. Finally, he arrives, conducts his survey, turns around, and makes the long journey home. From Bob's perspective, the round trip takes 5 years. He experiences 5 years of mission time. 5 birthdays pass. He ages 5 years. But when Bob returns to Earth and steps out of his spacecraft, he gets a shock. Alice is not 35 years old. She's 41. 11 years have passed on Earth. While Bob experienced only 5 years aboard his spacecraft, Bob has aged 5 years. Alice has aged 11. Bob is now biologically younger than his twin sister by 6 years. This thought experiment is called the twin paradox, and it's one of the most famous examples of time dilation in special relativity. At first glance, it seems paradoxical. After all, motion is relative, right? From Bob's perspective, isn't it Alice who's moving away at 90% the speed of light? Shouldn't Alice's clock appear to run slow from Bob's perspective? Shouldn't Bob think Alice is the one who ages less? This is where the paradox comes from. If motion is relative, why isn't the effect symmetrical? Why does Bob definitively age less than Alice, rather than each twin thinking the other aged less? The resolution lies in acceleration. Bob's journey is not symmetrical to Alice's. Bob accelerates at the start of his journey. He decelerates when he reaches his destination. He accelerates again for the return trip. He decelerates when arriving back at Earth. Bob changes reference frames and experiences forces. Alice does not. She remains in an inertial reference frame, meaning she isn't accelerating. Technically, she's in Earth's gravitational field and rotating with the planet, but for this thought experiment, we treat those effects as negligible. This breaks the symmetry. The situation is not equivalent. Bob genuinely ages less. It's not perspective. It's not illusion. Bob has traveled through less time than Alice. When Bob returns, he has effectively traveled into Alice's future. He skipped 6 years of Earth's timeline. Everyone on Earth, Alice, his friends, his family, society at large, aged 6 years more than he did. This is time travel. Not backward. Relativity doesn't allow traveling to the past, but forward. Bob jumped forward through time by traveling at high speed. The twin paradox isn't really a paradox at all. It's a demonstration of a genuine, measurable physical effect. Time flows at different rates depending on motion and acceleration. And this effect has two components: time dilation due to velocity and time dilation due to gravity. Let's explore each one. Time dilation due to velocity, also called kinematic time dilation or special relativistic time dilation, is conceptually straightforward once you accept Einstein's postulate. The speed of light is constant for all observers. The faster you move relative to an observer, the slower your clock ticks from that observer's perspective. Let's build intuition with examples at different speeds. Imagine you're on a spacecraft traveling at 10% the speed of light, about 30,000 kilometers per second. Ridiculously fast by human standards. At this speed, time dilation is about half of 1%. If you travel for 1 year at this speed, you'd age about 1.8 days less than someone stationary. Noticeable, but not dramatic. Now increase the speed to 50% the speed of light. Time dilation increases to about 13%. Travel for 1 year at this speed, and you age about 47 days less than a stationary observer. Nearly 2 months of time dilation over 1 year of travel. At 70% the speed of light, time dilation jumps to about 30%. 1 year of your time equals about 1.4 years for a stationary observer. At 90% the speed of light, the speed in our twin paradox example, time dilation becomes dramatic. Time slows to less than half. 1 year for you equals about 2.3 years for a stationary observer. At 99% the speed of light, time crawls to about 1/7 its normal rate. 1 year for you equals about 7 years for Earth. Sound familiar? That's the ratio from Interstellar's Miller's planet, though there it's caused by gravity rather than speed. At 99.9% the speed of light, time slows even more dramatically. 1 year for you equals about 22 years on Earth. And at 99.999% the speed of light, speeds achieved by particles in modern accelerators, time becomes almost frozen. 1 year for you could equal hundreds or thousands of years for a stationary observer. There's a mathematical factor that governs this relationship. Physicists call it the Lorentz factor, named after Hendrik Lorentz, who derived the mathematical transformations before Einstein provided the physical interpretation. Without getting into the mathematics, because I promised conceptual understanding, not equations, the essence is this. As your velocity approaches the speed of light, time dilation approaches infinity. At exactly the speed of light, time would stop completely. But, and this is crucial, nothing with mass can actually reach the speed of light. The closer you get, the more energy it takes to accelerate further. It would require infinite energy to accelerate any massive object to light speed. Light itself travels at light speed, obviously. But photons, particles of light, have no mass. That's why they can travel at that speed. For anything with mass, the speed of light is an asymptotic limit. You can get closer and closer, but you can never quite reach it. This speed limit isn't arbitrary. It's baked into the structure of space-time itself. The speed of light isn't just the speed that light happens to travel. It's the speed of causality, the maximum speed at which cause can lead to effect, at which information can propagate through the universe. Time dilation due to velocity is sometimes described using the metaphor of trading motion. Through space for motion, through time. Imagine you're always moving at a constant speed through four-dimensional space-time. When you're stationary in space, all your motion is through time. You age at maximum rate. When you move through space, some of your motion gets redirected from the time dimension to spatial dimensions. You age slower. It's not a perfect metaphor, but it captures something essential. There's a trade-off between motion through space and motion through time. Now, you might be wondering, why don't we notice this in everyday life? Because everyday speeds are tiny compared to the speed of light. When you walk at 5 kilometers per hour, or drive at 100 kilometers per hour, or fly in an airplane at 900 kilometers per hour, these speeds are insignificant fractions of light speed. Light travels at about 1,080,000,000 kilometers per hour. Your car is moving at about 0.00009% the speed of light. At everyday speeds, time dilation is vanishingly small. To notice it, you need atomic clocks accurate to nanoseconds or better. You need to measure time to 9, 10, 11 decimal places. But it's there. It's real. And we've measured it. But velocity-based time dilation is only half the story. There's a second type of time dilation, one that's arguably even more profound: gravitational time dilation. Einstein didn't rest after special relativity. He knew his theory was incomplete. Special relativity dealt with observers moving at constant velocities, inertial reference frames. But what about acceleration? What about gravity? For 10 years, Einstein wrestled with the problem of gravity. In 1915, he finally published his answer: general relativity. General relativity is one of the most elegant and profound theories in physics. Its central insight is that gravity is not a force in the traditional sense. Gravity is curvature of space-time. Imagine space-time as a flexible fabric, like a stretched rubber sheet. Place a massive object on this fabric, and it creates a dimple, a depression, a curvature. Smaller objects moving near this curvature follow curved paths, not because a force is pulling them, but because they're following the curved geometry of space-time itself. This is gravity. Not a force reaching across space to pull objects together, but the natural motion of objects through curved space-time. And here's the crucial point. When massive objects curve space-time, they curve both space and time. Gravity doesn't just affect how objects move through space. It affects how objects move through time. The stronger the gravitational field, the deeper you are in a gravity well, the slower time flows. Think of it this way. Massive objects create a time dip in the same way they create a spatial curvature. The closer you get to the massive object, the deeper into the time dip you fall, the slower your clock ticks relative to someone far away. This is gravitational time dilation, and it's fundamentally different from velocity-based time dilation. With velocity-based time dilation, the effect is reciprocal. If Bob sees Alice's clock running slow, Alice sees Bob's clock running slow too. Each observer measures the other's time as dilated. But gravitational time dilation is not reciprocal. Both observers agree on which clock is running slower. The clock deeper in the gravitational well, closer to the massive object, runs slower, and everyone agrees on this. If you're standing on Earth's surface and I'm hovering in a spaceship far above, we both agree that your clock is ticking slower than mine. There's no ambiguity, no perspective dependence. Gravity genuinely slows time. The stronger the gravitational field, the more pronounced the effect. On Earth's surface compared to far out in space, time flows slower by about 1 part in a billion. Tiny but measurable. Near the sun's surface, time flows about 2 parts in a million, slower than far from the sun. Near a neutron star, the collapsed remnant of a massive star, with gravitational fields billions of times stronger than Earth's, time dilation becomes substantial. Time could flow 20 or 30% slower near the surface compared to far away. Near a black hole, time dilation becomes extreme. Time can slow to a fraction of its normal rate. And at the event horizon of a black hole, the point of no return, time dilation becomes infinite. From the perspective of a distant observer, time stops completely at the horizon. Gravitational time dilation has profound implications. It means there is no universal now. Different locations in a gravitational field experience time at different rates. Your now and my now can be genuinely different if we're at different depths in a gravity well. It means time is not a backdrop against which events occur. Time is part of the fabric of the universe, woven together with space into space-time, and that fabric can be stretched and compressed by mass and energy. This revelation, that time itself can be manipulated by gravity, ranks among humanity's greatest intellectual achievements. It's as profound as discovering Earth orbits the sun, or that species evolve, or that matter is made of atoms. And unlike some abstract theories, gravitational time dilation has immediate practical consequences. It's happening right now, all around you, on Earth. Right now, as you sit or stand reading this, your head is aging faster than your feet. I'm completely serious. Your feet are closer to Earth's center of mass. They're slightly deeper in Earth's gravitational well. The gravitational field is marginally stronger at your feet than at your head, about 1 or 2 meters higher up. This difference in gravitational field strength causes a difference in time flow. Time ticks infinitesimally slower at your feet than at your head. How much slower? Over the course of 79 years, an average human lifespan, your feet would age about 90 billionths of a second less than your head. 90 nanoseconds, about the time it takes light to travel 27 meters. This difference is so microscopically small that it has zero practical impact on your life. Your feet aren't going to look noticeably younger than your face. You won't develop asymmetrical wrinkles from differential aging rates between body parts. But it's real. It's there. And incredibly, we've measured it. In 2010, scientists at the National Institute of Standards and Technology in Boulder, Colorado, conducted one of the most precise measurements of gravitational time dilation ever performed. They took 2 identical atomic clocks. These weren't ordinary clocks. These were optical lattice clocks, among the most precise timekeeping devices ever created. These clocks are so accurate that they would lose less than 1 second over the entire age of the universe, 14 billion years. The scientists placed one clock on a lab bench. They placed the second clock on a platform 33 centimeters higher. 33 centimeters, about the distance from your waist to your chest, a step on a staircase. They let both clocks run, measuring time with incredible precision. And they found a difference. The higher clock ticked faster. Over a period of measurement, it gained time relative to the lower clock. The effect was tiny, about 4 parts in 100 quintillion per second, but it was unmistakably there. Extrapolated over 79 years, the higher clock would gain about 90 nanoseconds. This experiment proved something philosophers had debated for millennia. Time is not uniform across even short distances. Time flows at different rates mere centimeters apart. This means if you've spent your entire life sleeping on the top bunk while your sibling slept on the bottom bunk, you're technically a few nanoseconds older than your sibling would be if you'd switched positions. If you live in a penthouse apartment on the 50th floor while your friend lives in a basement, you age faster by a tiny amount than your friend. If you live in Denver, Colorado, at 1,616 meters above sea level, while someone else lives at sea level in New York City, you age faster by about 5 microseconds per year. Over a 70-year lifespan, that's about 350 microseconds, about a third of a millisecond. Still negligible in human terms, but measurable, real, present. This phenomenon extends everywhere. Time ticks faster at the top of mountains than in valleys, faster at high altitudes than at sea level, faster in an airplane than on the ground. Conversely, time ticks slower underground, slower in deep mines, slower at the bottom of the ocean. Gravity literally compresses time, and we don't need theoretical thought, experiments to know this. We've measured it directly. With atomic clocks, in laboratories, on mountains, in airplanes, which brings us to one of the most elegant experiments in the history of physics. October 1971. Two physicists, Joseph Havel and Richard Keating, had an audacious plan. They wanted to test Einstein's predictions about time dilation, both velocity-based and gravitational, using the most accurate clocks available at the time, cesium beam atomic clocks. Their plan was simple in concept, complex in execution. Fly atomic clocks around the world on commercial airliners and compare them to identical clocks that stayed on the ground. They obtained 4 cesium beam atomic clocks. These devices were the cutting edge of timekeeping technology in 1971, accurate to about 1 nanosecond, 1/1000th of a second per day. 4 clocks would fly eastward around the world. 4 would fly westward. 4 would stay at the United States Naval Observatory in Washington, D.C. as controls. Why eastward and westward? Because Earth is rotating. Flying eastward means flying in the same direction as Earth's rotation. You're moving faster relative to Earth's center. Flying westward means flying against Earth's rotation. You're moving slower relative to Earth's center. This difference in velocity should cause different amounts of velocity-based time dilation for the eastward and westward clocks. Additionally, the airplane flies at altitude, about 10,000 meters up, where gravity is slightly weaker than at sea level. This should cause gravitational time dilation that makes the airborne clocks tick faster than ground clocks. Einstein's theories predicted specific amounts of time dilation for each flight. Havel and Keating calculated the numbers before the experiment. For the eastward flight, they predicted 2 things. First, the clocks would lose about 40 nanoseconds because they were flying faster. That's velocity time dilation. Second, the clocks would gain about 144 nanoseconds because they were at higher altitude. That's gravitational time dilation. Add them up, and you get a net gain of about 104 nanoseconds. For the westward flight, scientists predicted that the clocks would gain about 53 nanoseconds from velocity time dilation because the plane was moving more slowly, and about 179 nanoseconds from gravitational time dilation for a total gain of roughly 232 nanoseconds. The scientists boarded commercial flights, American Airlines and Transworld Airlines, carrying atomic clocks in passenger seats. They flew around the world over several days, carefully recording conditions and monitoring the clocks. When they returned and compared the traveled clocks to the stationary clocks, the results were clear. The eastward flying clocks had gained about 59 nanoseconds. The westward flying clocks had gained about 273 nanoseconds. Within experimental uncertainty, these results matched Einstein's predictions. Time dilation was real, measurable, confirmed. This experiment was revolutionary, not because it was the first test of relativity. Other experiments had tested specific aspects of Einstein's theories, but the Haffel-Keating experiment tested both special and general relativistic effects simultaneously. Using macroscopic clocks on ordinary commercial flights, it demonstrated that time dilation isn't some esoteric effect only visible in particle accelerators or astronomical observations. It happens on airplanes. On flights, you could book yourself. Since 1971, the experiment has been repeated with better clocks and more controlled conditions. Every repetition has confirmed the results. Time dilation is not controversial. It's not speculative. It's established physics, tested to extraordinary precision. But here's where the story gets really interesting, because Haffel and Keating's experiment wasn't just academic. It revealed something crucial for a technology that was being developed at exactly that time. A technology that would become essential to modern civilization. GPS. Pull out your phone. Open a map app. Watch as a little blue dot shows your exact location, accurate to within a few meters. You're holding a miracle of modern engineering, and it only works because we account for time dilation. The Global Positioning System, GPS, consists of approximately 31 satellites orbiting Earth at an altitude of about 20,000 kilometers. Each satellite carries an atomic clock, broadcasting the precise time along with its position. Your phone receives signals from multiple satellites. By comparing the arrival times of these signals and knowing the speed of light, your phone calculates its distance from each satellite. With signals from at least 4 satellites, it can determine your exact position on Earth's surface. This requires extraordinary precision. GPS signals travel at the speed of light, about 300,000 kilometers per second. A timing error of just 1 microsecond, 1/1,000,000th of a second, translates to a position error of about 300 meters. For GPS to achieve meter-level accuracy, satellite clocks must be synchronized to within about 10 nanoseconds of each other and of ground-based reference clocks. Here's the problem. Those satellites are moving fast, and they're high above Earth's surface. Both factors cause time dilation. Let's break down the numbers. First, velocity-based time dilation. GPS satellites orbit at about 14,000 kilometers per hour, roughly 3,889 meters per second. This is fast, but it's only about 0.0013% the speed of light. At this speed, special relativity predicts the satellite clocks will run slower than ground clocks by about 7 microseconds per day. 7/1,000,000ths of a second per day. Doesn't sound like much, but remember, light travels 300,000 kilometers per second. In 7 microseconds, light travels about 2,100 meters, over 2 kilometers. If we didn't correct for velocity-based time dilation, GPS positions would drift by multiple kilometers per day. Now add gravitational time dilation. The satellites are 20,000 kilometers above Earth's surface, where Earth's gravitational field is about 1/4 as strong as its sea level. According to general relativity, weaker gravity means time ticks faster. The satellite clocks tick faster than ground clocks by about 45 microseconds per day. Now, we have 2 competing effects. Velocity makes the satellite clocks run slower by 7 microseconds per day. Weak gravity makes the satellite clocks run faster by 45 microseconds per day. Net effect: 45 minus 7 equals 38 microseconds per day faster. GPS satellite clocks, if left uncorrected, would gain 38 microseconds per day compared to ground clocks. In 38 microseconds, light travels about 11.4 kilometers. Without correction, GPS positions would be off by over 11 kilometers after just 1 day. After a week, you'd have errors of nearly 80 kilometers. After a month, GPS would be utterly useless for navigation. So how did engineers solve this problem? Brilliantly. Before launching the satellites, they programmed the atomic clocks to tick slightly slower than they should. They set the clock frequency to 10.22999999994. 3 MHz instead of the standard 10.23 MHz. This precompensates for the time dilation the satellites will experience in orbit. Once in space, the combination of slower ticking due to velocity and faster ticking due to weak gravity brings the satellite clocks into synchronization with ground clocks. It's elegant, it's precise, and it's absolutely necessary. Without Einstein's theories, without understanding time dilation, GPS would not work. Period. Full stop. Every time you use your phone's map to navigate to a restaurant, you're relying on corrections for relativistic time dilation. Every time a ship crosses an ocean using GPS guidance, every time an airplane lands using GPS-assisted navigation, every time a delivery driver finds your address, all of it depends on the fact that time flows differently in orbit than on Earth's surface. Time dilation isn't abstract theory, it's infrastructure. It's embedded in technology that billions of people use every single day without thinking about it. GPS is perhaps the most visible everyday application of relativity, but it's not the only one. And it's not even the most dramatic demonstration of time dilation in action. Let me drive home just how critical time dilation corrections are for GPS, because this point cannot be overstated. The frequency adjustment I mentioned, setting satellite clocks to 10.22999999543 MHz, represents a change of about 4.465 parts in 10 billion. That's a tiny adjustment. About 0.000000045%. But that tiny adjustment prevents catastrophic errors. Here's what would happen without it. Day 1. Your position is off by 11.4 kilometers. Day 2. Your position is off by 22.8 kilometers. Week 1. Your position is off by about 80 kilometers. Month 1. Your position is off by about 340 kilometers. After 6 months, GPS would be telling you you're in a different state or country than you actually are? The system would be completely useless for any practical purpose. This isn't theoretical. When GPS was first being developed in the 1970s and early 80s, there was actually debate within the engineering community about whether relativistic corrections would be necessary. Some engineers thought the effects might be negligible. Others weren't sure the corrections would work as predicted. There was enough uncertainty that when the first GPS satellite, NTS-2, launched in 1977, it carried a switch. Engineers could toggle between normal clock frequency and relativistically corrected frequency. They turned on the satellite with normal frequency. Within hours, it became clear that the satellite clock was drifting out of sync with ground clocks. They flipped the switch to the corrected frequency. The drift stopped. The clock synchronized perfectly with ground clocks. Einstein was right. Relativity worked exactly as predicted. Since then, every GPS satellite has been launched with pre-corrected clock frequencies. It's standard engineering practice. Not controversial, not optional. Absolutely essential. But the corrections don't stop there. GPS receivers, the devices in your phone, your car, your watch, also perform additional relativistic corrections in real time. The satellites orbit Earth in elliptical paths, not perfect circles. This means their altitude varies slightly, which changes the gravitational time dilation they experience. Their velocity also changes slightly as they move through their orbits, faster when closer to Earth, slower when farther away, which changes the velocity-based time dilation. These variations need to be accounted for continuously. The GPS satellites broadcast information about their orbits, and receivers use this information to calculate precise relativistic corrections for each satellite at each moment. The math isn't particularly complex. The equations of general and special relativity for weak fields and moderate speeds are straightforward. But the fact that this math is running in every GPS receiver billions of times per day worldwide is extraordinary. Every time someone asks their phone for directions, Their device is solving Einstein's field equations. Time dilation has gone from revolutionary physics discovery to routine engineering calculation in less than a century. But GPS satellites aren't the only things in orbit experiencing time dilation. There are humans up there too. Humans who are aging at a different rate than the rest of us. 400 kilometers above your head, the International Space Station is orbiting Earth right now. It completes one orbit every 90 minutes, traveling at approximately 27,600 kilometers per hour. Inside, astronauts float in microgravity, conducting experiments, maintaining systems, exercising to counteract the effects of weightlessness, and occasionally gazing out windows at the breathtaking view of Earth below. And they're aging slower than you are. Not by much, but measurably, provably. Let's do the calculation. The ISS is moving at about 7,660 meters per second. That's about 0.0026% the speed of light. At this velocity, special relativity predicts time dilation of about 7 microseconds per 6 months. But the ISS is also at altitude, about 400 kilometers up, where Earth's gravitational field is about 11% weaker than at the surface. General relativity predicts this causes clocks to tick faster. However, and this is crucial for the ISS altitude, the velocity effect dominates. The speed of the station causes more time dilation than the altitude negates. Net result: astronauts aboard the ISS age slower than people on Earth's surface by about 5 milliseconds every 6 months, 5/100ths of a second, 0.5 of a second, about the duration of one frame in a 30 frames per second video. For every 6 months an astronaut spends aboard the ISS, they age 5 milliseconds less than someone on Earth. Now let me tell you about Scott Kelly. In 2015, NASA astronaut Scott Kelly embarked on a nearly year-long mission aboard the ISS, 340 consecutive days in space. This was part of NASA's twin study because Scott has an identical twin brother, Mark Kelly, also a NASA astronaut who had flown space shuttle missions but who stayed on Earth during Scott's long-duration flight. This created a perfect natural experiment. 2 genetically identical humans, one in orbit, one on the ground, allowing scientists to study the physiological effects of long-duration spaceflight, including time dilation. When Scott returned to Earth in March of 2016, he had aged about 10 milliseconds less than Mark. 10 milliseconds, 1/100th of a second. Scott Kelly traveled 10 milliseconds into Mark Kelly's future. Let me emphasize this. Scott Kelly is a time traveler. He jumped forward through time by spending a year moving at high speed in a weaker gravitational field. He experienced less time than his twin. He aged less. His biological clocks, his cellular processes, his heartbeat, all occurred fewer times than Mark's. 10 milliseconds is negligible in human terms. You wouldn't notice it. It doesn't give Scott any practical advantage or Mark any disadvantage. But conceptually, philosophically, it's profound. Time is not universal. Time is not the same for everyone. And Scott Kelly isn't even humanity's greatest time traveler. That honor belongs to Russian cosmonaut Sergei Krikalev. Krikalev holds the record for most cumulative time in space over multiple missions, 803 days total, spread across 6 flights between 1988 and 2005. 803 days traveling at high speed in orbit. By the time Krikalev retired, he had aged approximately 20 milliseconds less than he would have if he'd stayed on Earth. 20 milliseconds, 1/50th of a second. Sergei Krikalev is 20 milliseconds younger than he should be. He jumped 20 milliseconds into Earth's future. Russian cosmonaut Gennady Padalka holds a slightly longer cumulative time record, 879 days, making him about 22 milliseconds younger. These aren't thought experiments. These aren't projections or estimates. We can calculate the exact amount of time dilation experienced by every astronaut based on their orbital parameters and duration in space, and the predictions match observations perfectly. Time dilation is real, measurable, happening right now to people in orbit. But to really understand how dramatic time dilation can become, we need to look beyond human-made spacecraft. We need to look at nature's own demonstrations of time dilation. Particles created by cosmic rays traveling through our atmosphere at nearly the speed of light, living far longer than they should. Before we dive into cosmic particles, I want to make sure the scale of astronaut time dilation is clear, because it's easy to dismiss 20 milliseconds as so small it doesn't matter. And you're right. In practical, everyday human lifespan terms, 20 milliseconds of differential aging is completely negligible. But zoom out. Think about what it represents. Sergei Krikalev and Gennady Padalka didn't just experience slightly different aging, they experienced genuinely less time. Fewer heartbeats, fewer breaths, fewer thoughts. Their neurons fired fewer times. Their cells divided fewer times. If you could somehow count every molecular process, every biochemical reaction, every cellular event that occurred in their bodies during their time in space, you would find that they experienced measurably fewer of these events than someone on Earth. Time for them genuinely passed more slowly. And this wasn't because they were in some sort of suspended animation or cryogenic freeze. They were awake, conscious, active. They experienced their time normally. 1 second felt like 1 second to them, but less time occurred for them than for people on Earth. This is the profound weirdness of time dilation. It's not about perception or measurement tricks. Time itself flows at different rates. Now, 20 milliseconds over 800 days works out to about 0.000003% time dilation. Utterly tiny, but imagine if we could go faster, much faster. If an astronaut traveled at 10% the speed of light for 1 year, they'd age about 18 days less than Earth. At 50% light speed for 1 year, they'd age about 134 days less, almost 4.5 months. At 90% light speed for 1 year, they'd age about 280 days less, over 9 months. At 99% light speed for 1 year, they'd age about 351 days less. They'd experience about 14 days, while nearly a full year passed on Earth. These speeds are far beyond current technology. The fastest human-made object, NASA's Parker Solar Probe, reaches about 0.06% the speed of light at its closest approach to the Sun, nowhere near the speeds needed for dramatic time dilation. But nature achieves these speeds routinely. Cosmic rays, high-energy particles from supernovae, neutron stars, black holes, and other violent cosmic events, constantly bombard Earth's atmosphere at velocities approaching the speed of light. And when these particles collide with atmospheric molecules, they create secondary particles called muons. Muons that shouldn't reach Earth's surface, but they do, because of time dilation. Imagine you're a muon. You're born in the upper atmosphere, about 10 to 15,000 meters above Earth's surface, created when a cosmic ray proton slams into an atmospheric molecule with tremendous energy. You're a fundamental particle, similar to an electron, but about 200 times heavier. You carry a negative electrical charge. You're unstable. You won't last long. In fact, your half-life is only 2.2 microseconds, 2 millionths of a second. On average, half of all muons decay, transform into electrons and neutrinos within 2.2 microseconds. You're traveling downward at 99.4% the speed of light, about 298,000 kilometers per second. At this speed, you can travel about 660 meters in your 2.2 microsecond half-life. But you were created 10,000 meters up. According to classical physics without time dilation, you should decay long before reaching Earth's surface. Even if you're lucky and survive several half-lives, you should decay somewhere in the middle atmosphere. Very few muons should reach sea level, maybe 1 in a million, maybe fewer. But physicists set up detectors at sea level and count muons, and they find thousands of muons per square meter per minute. Far, far more than classical physics predicts. How is this possible? Time dilation. From our perspective on Earth, watching muons rain down from the sky at 99.4% light speed, the muons' clocks are ticking slowly. Their half-life appears stretched. Instead of 2.2 microseconds, we measure their effective half-life as about 20 microseconds, roughly 9 times longer. This extended half-life gives muons enough time to reach Earth's surface before decaying. We detect them in abundance because, from our frame of reference, they're living much longer than they should. Now here's where it gets really interesting. What does this look like from the muon's perspective? From the muon's frame of reference, its half-life is still 2.2 microseconds. It doesn't experience time dilation. Time flows normally for it. But from the muon's perspective, the distance to Earth's surface is contracted. Length contraction, a consequence of relativity related to time dilation, squeezes the 10,000-meter distance down to about 1,100 meters. The muon only needs to travel 1,100 meters in its 2.2 microsecond lifespan. That's achievable at 99.4% light speed. Same end result. Muons reach Earth's surface, but explained differently depending on which reference frame you're in. From Earth's frame, time dilation stretches muon lifespans. From muon's frame, length contraction reduces the distance to travel. Both descriptions are valid. Both are real. This is the essence of relativity. Different observers describe the same physical events differently, but all descriptions are equally correct. Scientists have measured this effect with extraordinary precision. In experiments at CERN, the European Particle Physics Laboratory, researchers have accelerated muons to various speeds and measured their decay rates at 99.94% the speed of light. Muons live about 29.3 times longer than muons at rest. At 99.99% the speed of light, muons live about 70 times longer. At 99.999% the speed of light, muons live hundreds of times longer. The effect scales exactly as special relativity predicts. Every particle accelerator in the world depends on time dilation. Protons, electrons, muons, and other particles circulating at near-light speeds live much longer than they would at rest, allowing them to complete millions of trips around the accelerator ring before decaying. Engineers designing accelerators must account for time dilation in their calculations. If they didn't, their predictions for particle lifetimes, collision rates, and detector responses would be completely wrong. The machines wouldn't work. Time dilation isn't a minor correction or a subtle effect in these environments. It's a dominant factor that must be incorporated into every aspect of particle physics. But even particle accelerators, as extreme as they are, can't match the most extreme time dilation environments in the universe. For that, we need black holes. Let me give you a sense of just how routine time dilation has become in particle physics. The Large Hadron Collider at CERN, buried 100 meters beneath the border between France and Switzerland, is a ring 27 kilometers in circumference. Inside this ring, protons travel at 99.999 to 991% the speed of light. At this velocity, time dilation reaches a factor of about 7,000. From our perspective in the laboratory, watching these protons zip around the ring, the protons' clocks tick 7,000 times slower than ours. For every 7,000 seconds that pass in the lab, about 1 hour and 57 minutes, only 1 second passes from the proton's perspective. If protons had lifetimes, they don't, they're stable particles. But if they did decay, they would appear to live 7,000 times longer than at rest. This isn't theoretical. We observe this with unstable particles all the time. Take pions. particles made of a quark and an antiquark bound together. Pions at rest have a half-life of about 26 nanoseconds. Accelerate pions to 99.9% the speed of light, and their half-life stretches to about 500 nanoseconds, about 19 times longer. Accelerate them further to 99.99% light speed, and their half-life extends to about 2 microseconds, about 77 times longer. Every prediction, every measurement, every collision event analyzed at particle accelerators around the world incorporates time dilation as a fundamental, essential component of the calculations. Particle physicists don't think about time dilation as some exotic effect. It's as routine as accounting for air resistance in ballistics or friction in mechanical engineering. In 2010, physicists at the GSI Helmholtz Center for Heavy Ion Research in Germany conducted an elegant test of time dilation using lithium ions. They accelerated lithium ions to 33.8% the speed of light in a storage ring. At this speed, time dilation predicts the ions should experience time about 6% slower than stationary ions. The researchers excited electrons in the lithium ions to higher energy states using lasers, then measured how long it took for the electrons to fall back to their ground state, emitting light in the process. For stationary lithium ions, this transition takes a specific, well-known amount of time. For moving lithium ions, the transition took longer, exactly as much longer as time dilation predicted. The experiment confirmed time dilation to an accuracy of better than 1%. Once again, Einstein's theory passed with flying colors. These aren't isolated experiments conducted once in specialized facilities. Time dilation effects are observed thousands of times per day in particle accelerators worldwide. Every PhD student in particle physics learns to calculate time dilation factors as a basic skill. It's as fundamental to particle physics as multiplication is to mathematics. But for all the impressive time dilation we can create in accelerators, for all the stretched lifetimes and slowed clocks we observe in fast-moving particles, these effects pale in comparison to what happens near the most extreme objects in the universe. Objects so dense, so massive, that they tear holes in the fabric of space-time itself, black holes. Before we journey to black holes, let's resolve something that might still be bothering you: the twin paradox. Remember Alice and Bob? Alice stayed on Earth, Bob traveled at high speed to a distant star and back, and Bob aged less. The paradox was, if motion is relative, why isn't the situation symmetrical? From Bob's perspective, couldn't he say Alice was the one moving away at high speed? Shouldn't Bob think Alice ages less? The resolution is subtle, but crucial. Bob's journey is not symmetrical to Alice's. Alice remains in an inertial reference frame. She is not accelerating, ignoring Earth's gravity and rotation for simplicity. She stays in one continuous reference frame for the entire journey. Bob accelerates at the start. He's in one reference frame while traveling away from Earth. Then he decelerates, turns around, and accelerates in the opposite direction for the return trip. He's in a completely different reference frame on the way back. Then he decelerates again when arriving at Earth. Bob changes reference frames. This breaks the symmetry. The key insight is that special relativity applies to inertial reference frames, observers moving at constant velocity. When you accelerate, you're changing frames. Special relativity alone can't handle acceleration. You need general relativity for that. When you properly account for the acceleration Bob experiences, the forces he feels when the spacecraft's engines fire, the mathematics of general relativity definitively show that Bob ages less. There's no ambiguity. Both Alice and Bob agree that Bob aged less. It's not perspective dependent. It's not reciprocal. Bob genuinely, objectively, measurably experienced less time. This has been tested experimentally with atomic clocks. The Haffel-Keating experiment we discussed earlier is essentially a real-world version of the twin paradox. The clocks that flew around the world on airplanes are like Bob. The clocks that stayed on the ground are like Alice. The results matched the predictions. The traveling clocks recorded less elapsed time or more, depending on the direction of flight and the balance between velocity and gravitational effects. The twin paradox isn't a paradox at all. It's a prediction of relativity that has been confirmed by experiment, and the implications are profound for potential interstellar travel. Imagine a spacecraft that can accelerate continuously at 1 Earth gravity, 9.8 meters per second squared. This acceleration would provide artificial gravity for the crew, making the journey comfortable. If this spacecraft accelerated for half the journey and decelerated for the second half, it could reach tremendous velocities near the midpoint. A trip to the center of our galaxy, 26,000 light-years away, would take about 26,000 years from Earth's perspective. But for the crew, experiencing time dilation throughout their high-speed journey? About 21 years? They would board the ship, experience 21 years of travel time, and arrive at the galactic center. When they looked back at Earth, 52,000 years would have passed. 26,000 years out, 26,000 years back, accounting for light travel time. Everyone they knew would be long dead. Human civilization might have risen and fallen. The Earth they left might be unrecognizable or even uninhabited. They would be travelers not just across Earth, but across time. This is the stark reality of relativistic travel. The universe allows you to travel vast distances in humanly reasonable timeframes, but only for you. Everyone you leave behind ages normally. You're escaping into their future. Science fiction has explored this scenario repeatedly. Joe Haldeman's novel, The Forever War, features soldiers fighting a centuries-long war, but experiencing only a few years subjectively due to relativistic travel between battles. They return to an Earth transformed beyond recognition, generation after generation. Ursula K. Le Guin's Rokanan's World features characters who travel between stars, aging only slightly while decades pass for others. These aren't just narrative devices. They're genuine consequences of relativity, explored through fiction because we don't yet have the technology to experience them in reality. But the physics is sound. Time dilation is real. If we ever develop near-light-speed propulsion, these effects will be unavoidable. Now, let's look at the most extreme time dilation environments in the known universe. A black hole is what happens when so much mass compresses into such a small volume that the curvature of space-time becomes extreme beyond imagination. When a massive star, say 20 or 30 times the mass of our Sun, exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core implodes in a fraction of a second. If the core is massive enough, nothing can stop the collapse. No force in nature is strong enough to resist. The core collapses past the density of atomic nuclei, past the density of neutron stars, past any density we can comprehend. It collapses to a point, a singularity where density becomes infinite and the known laws of physics break down. But before reaching the singularity, the collapsing matter crosses a boundary called the event horizon. This is the point of no return. Inside the event horizon, escape velocity exceeds the speed of light. Since nothing can travel faster than light, nothing inside can escape. Not matter, not light, not information. The event horizon isn't a physical surface. There's nothing there, no wall, no barrier. It's simply a boundary in space-time. Cross it going inward, and you can never cross it going outward. And at the event horizon, time dilation becomes infinite. Let me explain what this means. Imagine you're watching a clock fall toward a black hole. As the clock gets closer to the event horizon, time dilation increases. The clock appears to tick slower and slower. At twice the event horizon radius, the clock ticks noticeably slower, maybe half its normal rate. At 1.5 times the horizon radius, the clock is ticking at maybe 1/3 its normal rate. As the clock approaches closer and closer to the event horizon, it slows more and more. At the event horizon itself, from your perspective, watching from far away, the clock stops. Time dilation reaches infinity. The clock appears frozen. Not only does the clock stop ticking, the light from the clock becomes infinitely redshifted and infinitely dimmed. The clock fades from view, becoming darker and darker, redder and redder, until it's invisible. From your perspective, the clock never quite crosses the horizon. It hangs there, frozen in time, gradually fading into imperceptibility. This is true for anything approaching the horizon. A falling astronaut would appear to slow down, stop, and fade away. You would never actually see them cross the horizon. But from the astronaut's perspective, something completely different happens. The astronaut doesn't feel anything special at the horizon. They don't slow down from their own perspective. Time continues flowing normally for them, 1 second per second, as always. They cross the event horizon in a finite, relatively short amount of time. They continue falling inward. They experience the increasingly strong tidal forces, the difference in gravitational pull between their head and feet. That stretch them along the radial direction and compress them perpendicular to it, a process gruesomely called spaghettification. Eventually, they hit the singularity at the center. From their perspective, this journey from horizon to singularity takes a finite time, maybe seconds or minutes depending on the black hole's mass. Two observers, two completely different experiences, both valid, both real. This is the profound strangeness of black holes. Time itself becomes distorted so severely that different observers see entirely different sequences of events. And this isn't hypothetical. We've observed black holes. We've measured their masses. We've seen matter spiraling into them. We've even photographed the shadow of a black hole's event horizon against the glowing accretion disk surrounding it. Everything we observe matches general relativity's predictions. Time dilation near black holes is real. And in Christopher Nolan's Interstellar, this reality is explored with remarkable scientific accuracy. Let's return to the scene that opened this video. Miller's planet. 1 hour equals 7 years. Is this actually possible? The scientific consultant for Interstellar was Kip Thorne, a Nobel Prize-winning theoretical physicist and one of the world's leading experts on general relativity, black holes, and gravitational waves. Thorne worked closely with Christopher Nolan to ensure the film's depiction of black holes and time dilation was as accurate as possible. And Thorne's verdict? Yes, with the right conditions, Miller's planet's extreme time dilation is theoretically possible. Here's how it works. Miller's planet orbits Gargantua, a supermassive black hole. Thorne calculated that Gargantua must have a mass of approximately 100 million times the mass of our Sun. For perspective, that's enormous even by black hole standards. The supermassive black hole at the center of our Milky Way galaxy, Sagittarius A star, has a mass of only about 4 million solar masses. Gargantua is 25 times more massive. With 100 million solar masses, Gargantua's event horizon has a circumference of about 1 billion kilometers, roughly the same as Earth's orbital distance from the Sun. The horizon's radius, defined as circumference divided by 2 pi, is about 150 million kilometers. Gargantua is staggeringly huge. Now, for extreme time dilation to occur, Miller's planet must orbit very close to the event horizon. We're talking about being just barely outside the point of no return. But there's a problem. For a non-rotating black hole, a Schwarzschild black hole, the innermost stable circular orbit is at 3 times the event horizon radius. Any closer, and orbits become unstable. The planet would spiral inward and cross the horizon. At 3 times the horizon radius, time dilation is significant, but nowhere near the 60,000 to 1 ratio needed for 1 hour to equal 7 years. So Thorne invoked a rotating black hole. A Kerr black hole named after physicist Roy Kerr, who discovered the solution to Einstein's equations for rotating black holes. A rotating black hole drags space-time around with it in a phenomenon called frame dragging. Near the horizon, this dragging becomes so severe that anything, even light, must circle the black hole in the direction of rotation. This frame dragging allows stable orbits to exist much closer to the event horizon than for non-rotating black holes. For a maximally rotating black hole, the innermost stable orbit can be right at the event horizon itself. And at the event horizon of a rapidly rotating black hole, time dilation approaches infinity. Thorne calculated the exact conditions needed. Gargantua must be spinning at very nearly the maximum possible rate. The maximum is defined by the point where the black hole's rotation would cause the horizon to disappear, exposing the singularity, a naked singularity that most physicists believe is forbidden by nature. Gargantua must spin at less than the maximum by only about 1 part in 100 trillion. 99.9999999% of maximum. Spinning incredibly, almost impossibly, but not quite maximally fast. With this spin rate, and with Miller's planet in an orbit at the absolute closest stable distance from the horizon, the 1 hour equals 7 years time dilation becomes mathematically possible. The ratio works out to a time dilation factor of approximately 60,120 to 1. From Miller's planet's perspective, from the crew's perspective on the surface, time flows normally. 1 second per second. They experience 1 hour. But from the perspective of the Endurance ship orbiting safely far from Gargantua, time on Miller's planet crawls at 1/60,000th its normal rate. 7 years pass. The physics is accurate. Kip Thorne's calculations, using the full machinery of general relativity, applied to a rapidly rotating Kerr black hole, confirm this is possible. Now, let's address the caveats. Because while the time dilation of Miller's planet is physically possible, actually placing a habitable planet in such an orbit faces enormous challenges. First, tidal forces. Tidal forces are the difference in gravitational pull between the near side and far side of an object. Near a black hole, even a supermassive one like Gargantua, tidal forces become extreme. The side of Miller's planet facing Gargantua experiences significantly stronger gravity than the far side. For a planet at the distance required for that extreme time dilation, tidal forces would be tremendous. The planet would be stretched along the radial direction and compressed perpendicular to it. For a rocky planet with structural strength, this might not immediately tear it apart. Supermassive black holes have weaker tidal forces at their event horizons than stellar mass black holes because the horizon is so much farther from the singularity. But it would create massive stresses. Earthquakes, volcanic activity, possibly deformation of the planet's shape. Whether a planet could remain intact and habitable under such conditions is questionable. Second, Gargantua would likely have an accretion disk, material spiraling into the black hole, heated to millions of degrees by friction, emitting intense X-rays and gamma rays. Miller's planet, orbiting so close, would be bathed in this radiation, lethal levels of radiation, sterilizing the surface, evaporating any atmosphere. Life as we know it couldn't survive. In Interstellar, Miller's planet has liquid water, an atmosphere, and conditions compatible with at least brief human presence. In reality, these conditions are unlikely, perhaps impossible, at such proximity to an active black hole. Third, orbital stability. Even with frame dragging allowing closer orbits, a planet that close to the event horizon would be perpetually at risk of perturbations that could send it spiraling inward. Any interaction with other objects, asteroids, comets, other planets, could destabilize the orbit. The gravitational influence of nearby matter in the accretion disk could perturb the orbit over time. Maintaining a stable orbit for the millions or billions of years needed to develop an ocean-covered world with water seems implausible. So while the time dilation is accurate, the habitability is not. But here's the important point. Christopher Nolan and Kip Thorne knew this. They made deliberate choices to prioritize the emotional impact and narrative requirements of the story. Nolan wanted, as he put it, it was non-negotiable, the 1 hour equals 7 years time dilation. That extreme ratio was essential to the emotional gut punch of the scene, to the tragedy of Cooper losing years with his daughter while experiencing only brief time himself. Thorne showed Nolan that this was physically possible with the right black hole parameters. They used accurate physics for the time dilation. They chose to hand-wave the radiation and tidal force issues because addressing them would undermine the story. Sometimes storytelling requires selective realism. What matters is this: the core concept that gravity can slow time to such extreme degrees near a black hole is real physics. Confirmed. Established, Interstellar brought this reality to a mainstream audience in a visceral, emotional way that no documentary or textbook ever could. Millions of people who watched that film experienced, at least vicariously, what extreme time dilation would feel like. They felt the horror of missing decades of loved ones' lives in what seemed like moments. That's powerful science communication, and it's based on real, testable, experimentally confirmed physics. Time dilation isn't science fiction. It's science fact, dramatized for the screen. Let's think seriously about what time dilation means for humanity's future in space. If we ever develop the capability for interstellar travel, and that's an enormous if, given the staggering energy requirements, time dilation will be an unavoidable reality for space travelers. Consider a mission to Proxima Centauri, our nearest stellar neighbor, at approximately 4.2 light-years away. With current technology, such a trip would take tens of thousands of years, completely impractical for crewed missions. But suppose we develop a spacecraft capable of traveling at 90% the speed of light. At this velocity, time dilation becomes significant. Time slows to about 44% of its normal rate. From Earth's perspective, the trip to Proxima Centauri would take about 4.7 years, 4.2 light-years of distance divided by 0.9 times the speed of light. But for the crew, experiencing time dilation throughout the journey, about 2.1 years. The crew experiences just over 2 years of travel time, while nearly 5 years pass on Earth. Add the return trip, and the crew experiences about 4.2 years total, while over 9 years pass on Earth. The crew leaves in 2030. They experience 4.2 years. They return in 2039. Everyone they knew has aged 9 years. Their families, friends, colleagues, all nearly a decade older. Now increase the distance. Alpha Centauri system's closest approach to us varies slightly. Let's say 4.4 light-years. Or let's target a more interesting destination. Tau Ceti, 12 light-years away, which might have habitable planets. At 90% light speed, the trip takes about 13.3 years from Earth's perspective, but only about 5.9 years for the crew. Round trip, about 11.8 years crew time, 26.6 years Earth time. Launch in 2030. Return in 2056. You've aged 12 years. Everyone on Earth has aged 27 years. Your children are adults. Your spouse is middle-aged. The world has changed. Now pushed to 99% light speed. Time dilation increases dramatically to about 14% of normal. A trip to Tau Ceti and back, about 24.5 years Earth time, but only about 3.4 years crew time. You leave at age 30. You experience 3.4 years. You return at biological age 33.4. But it's 24.5 years later on Earth. Your twin sibling is now 54 years old. Your parents are elderly or deceased. Your young children are now adults with children of their own. You've become a stranger to your own family. This is the psychological cost of relativistic travel. Even modest time dilation creates temporal displacement. You don't just travel through space, you travel through time, skipping forward into everyone else's future. Science fiction writer Joe Haldeman explored this brilliantly in The Forever War. Soldiers fighting an interstellar war travel at relativistic speeds between battles. Each battle might last days or weeks from their perspective, but decades or centuries pass on Earth between engagements. Soldiers return from a war that lasted 2 years subjectively to find Earth changed beyond recognition, hundreds of years having passed. The society they fought to defend no longer exists. The cause they fought for has been forgotten. They're anachronisms, ghosts from a bygone era. Ursula K. Le Guin's early story Semley's Necklace features a character who travels by spacecraft for what feels like a single night, only to return and discover 16 years have passed. Her husband is dead. Her daughter has grown up without her. These stories aren't just exploring the technology of faster-than-light travel. They're exploring the human cost of time dilation, the loneliness, the disconnection, the irreversible loss. If humanity ever ventures to the stars at relativistic speeds, these issues will be real. Mission planners will have to account not just for the engineering challenges, but for the psychological and social challenges of temporal displacement. Astronauts leaving for decade-long missions will have to accept that they may return to a changed world. They'll age years while their families age decades. Some might see this as an advantage, a way to see the future, to skip ahead to see what civilization becomes. Others might see it as unbearable, to lose connection with everyone you love, to become unstuck from your own time. Either way, it's a consequence of relativity that can't be avoided. Time dilation isn't optional. It's baked into the structure of space-time. If we travel fast, we experience less time. That's the deal the universe offers us. And it's not just speculation, it's physics. Even without near light-speed travel, time dilation will become increasingly relevant as humanity expands into the solar system and potentially beyond. Consider a crewed mission to Mars. The trip takes about 7 months each way with current propulsion technology. The spacecraft's velocity, tens of thousands of kilometers per hour, causes microseconds of time dilation over the journey. Negligible? Yes, but measurable? Also yes, for scientific experiments requiring precise timing. Synchronization between Earth and Mars, certain physics experiments, astronomical observations, navigation systems, these microseconds might matter. Moreover, Mars orbits at a different distance from the Sun than Earth. The Sun's gravitational field is slightly different at Mars's orbital distance. This causes a tiny gravitational time dilation difference between Earth and Mars. Again, microseconds over a year. But for long-term Martian settlements, these small differences accumulate. A person born, raised, and living their entire 80-year life on Mars would experience a few milliseconds more or less time than their Earth-based twin, depending on the balance of velocity effects from Mars's orbital motion and gravitational effects from the Sun's field. Completely negligible in human terms, but conceptually significant. Now imagine multiple settlements, moonbase, Mars colony, orbital habitats at various locations, mining operations in the asteroid belt, outposts on the moons of Jupiter and Saturn. Each location has slightly different gravitational potential and orbital velocity. Each experiences time at a minutely different rate. For a distributed human civilization spanning the solar system, coordinating a universal now becomes surprisingly complex. Not impossible, atomic clocks and relativity calculations can account for it, but non-trivial. Communication delays already complicate solar system civilization. Light takes minutes to travel between planets. Add time dilation on top, and the concept of simultaneity becomes even more fluid. Missions to the outer solar system face more significant time dilation. A spacecraft traveling to the Kuiper Belt or beyond at higher velocities might experience weeks less time than Earth over a multi-decade mission. Small but growing. The effects scale with velocity and duration, and if huge. If we ever attempt missions to nearby stars, Even at modest fractions of light speed, time dilation becomes significant. A mission at 20% light speed to the nearest stars would involve noticeable time dilation, maybe a few weeks difference over a 20-year voyage. At 50% light speed, we're talking about years of difference. These aren't just numbers, they're years of life, years of aging, years that travelers don't experience, but their families back home do. Space agencies planning such missions will need to consider the psychological support needed for crews returning to a changed Earth, the social structures to maintain connections across temporal displacement, the ethical implications of sending people on journeys that will separate them from their own time. Time dilation will transition from physics curiosity to engineering constraint to social challenge. But beyond the practical considerations, time dilation forces us to confront deep questions about the nature of reality itself. For millennia, humans have pondered the nature of time. What is it? Does it flow? Does it exist independently of events? Or is it merely a way we order our experiences? Different philosophers proposed different answers. Some viewed time as absolute, a universal river carrying all of us along at the same rate. Others viewed time as subjective, a construct of consciousness varying from person to person. Einstein's relativity provides a definitive answer, at least within its domain of applicability. Time is not absolute. Time is not universal. Time is not independent of space. Time is a dimension of space-time, interwoven with the 3 dimensions of space into a 4-dimensional fabric. This fabric can be curved by mass and energy. It can be stretched and compressed. Different paths through space-time correspond to different amounts of elapsed time. The length of a path through space-time, technically called the proper time along that path, is what a clock traveling that path measures. This means there is no universal now, no moment that is the present throughout the entire universe. Your now and an astronaut's now are different. Your now and someone near a black hole's now are profoundly different. Simultaneity is relative. Events that appear simultaneous to one observer may not appear simultaneous to another observer moving relative to the first. This shatters our intuitive notion of time as a universal coordinating principle. It means the universe doesn't have a single timeline. It has countless timelines, one for each possible path through space-time. Think of space-time as a landscape. Different paths through this landscape correspond to different amounts of elapsed time. Some paths are longer, some are shorter. But longer and shorter here mean more elapsed time or less elapsed time. A clock traveling a shorter path through space-time experiences less time. This is why a fast-moving clock ticks slower. It's taking a different path through space-time, a path with less elapsed proper time. This is why a clock deep in a gravitational well ticks slower. Again, a different path through space-time with less elapsed proper time. There's no preferred path, no correct amount of time. All paths are equally valid. Your experience of time is real. An astronaut's experience of time is real. They're simply different because you're traveling different paths through space-time. This realization that time is not a universal external framework, but a dimension of space-time that different observers traverse differently, ranks among humanity's most profound intellectual achievements. It's on the same level as the Copernican revolution, which taught us Earth is not the center of the universe, or Darwin's evolution, which taught us humans are not separate from nature, but products of natural processes. Relativity teaches us that time itself is not absolute, but woven into the dynamic fabric of reality. And yet, for all its philosophical profundity, relativity is eminently practical, testable, observable, technological. It's verified by GPS satellites, by atomic clocks, by particle accelerators, by astronomical observations of binary pulsars, gravitational waves, light bending around the sun. Time dilation is both mind-bendingly weird and utterly mundane, both extraordinary and everyday. This duality is part of what makes physics beautiful. Here's what's extraordinary about time dilation. It seems impossible, yet it's real. Our intuitions, honed by millennia of experience at low speeds and weak gravitational fields, scream that time should be absolute. 1 second should equal 1 second for everyone, everywhere, always. But the universe doesn't care about our intuitions. The universe operates according to its own rules. And those rules say, time is flexible. What makes relativity so powerful, what elevates it from philosophical speculation to established science, is that it makes precise, testable predictions. Einstein didn't just say time is relative. He provided equations, mathematics, specific predictions for exactly how much time dilation occurs under any given conditions. And then, scientists tested those predictions. Haffel and Keating flew atomic clocks on airplanes. The clocks gained and lost time exactly as predicted. Particle physicists measured muon decay rates at high velocities. The lifetimes stretched exactly as predicted. GPS engineers corrected satellite clock frequencies. The system works exactly as predicted. Astronomers observed binary pulsars, pairs of neutron stars orbiting each other at relativistic speeds. The orbital decay due to gravitational wave emission matches Einstein's predictions to within 0.2%. LIGO detected gravitational waves, ripples in space-time itself caused by merging black holes. The waveforms match general relativity's predictions with extraordinary precision. Every test confirms Einstein's theories. Every measurement matches predictions. Time dilation isn't controversial among physicists. It's not debated. It's established. It's as well confirmed as any scientific theory in history. And yet, it remains deeply weird. The fact that moving clocks tick slower, that gravity slows time, that identical twins can age at different rates, that you can travel to the future by moving fast. These truths are so contrary to everyday experience that they feel like science fiction, but they're science fact. This is the power of physics, to reveal truths about reality that are utterly unexpected, yet rigorously provable. Our intuitions are wrong. Our common sense assumptions about time are incorrect. The universe is stranger than we imagined, but it's also comprehensible. We can understand it. We can model it mathematically. We can test our models. We can confirm that our equations match reality. Einstein figured this out with thought experiments and mathematics, working in a patent office with no access to sophisticated experimental equipment. He imagined riding alongside a light beam. He thought about how observers in different reference frames would perceive events. He followed the logical consequences of simple postulates, and he derived the flexible nature of time through pure thought. Then, over the following century, thousands of physicists tested his predictions in laboratories, in space, in particle accelerators, using atomic clocks and GPS satellites and telescopes, and every test confirmed Einstein was right. This is science at its finest. Radical ideas, rigorously tested, confirmed by evidence. Time is not what we thought it was, and we figured that out. But for all we've learned, there's still so much we don't know. Einstein's theories, special and general relativity, are extraordinarily successful. They've passed every experimental test for over a century, but we know they're incomplete. There are regimes where general relativity breaks down, where the equations produce nonsensical results, where our understanding fails. The singularity at the center of a black hole is one such place. General relativity predicts infinite density, infinite curvature, infinite tidal forces. Infinite is physics unspeak, for our theory is failing here. Real physical quantities shouldn't be infinite. Inside a black hole, general relativity can't tell us what actually happens. The theory breaks down. The Big Bang is another such place. Trace the universe backward in time, And general relativity predicts everything came from a singularity, a point of infinite density and temperature. Again, infinite suggests the theory is reaching its limits. The deepest issue is that general relativity and quantum mechanics, our two most successful theories, are fundamentally incompatible. General relativity describes gravity as smooth, continuous curvature of spacetime. It's a classical theory, meaning it doesn't incorporate quantum effects. Quantum mechanics describes matter and energy as fundamentally discrete, probabilistic, subject to uncertainty principles. It works beautifully for electromagnetism, the strong nuclear force, the weak nuclear force, but it doesn't include gravity. Combining these theories, creating a theory of quantum gravity, is one of the greatest unsolved problems in physics. We need quantum gravity to understand what happens inside black holes, what happened in the first moments of the Big Bang, how space-time itself behaves at the smallest scales, and we need quantum gravity to fully understand time itself. Does time emerge from something more fundamental? Is space-time quantized, made of discrete chunks rather than being smooth? Does time exist at the Planck scale, or does it break down into something stranger? We don't know. String theory, loop quantum gravity, and other approaches to quantum gravity are being explored, but we don't yet have experimental evidence to distinguish between them. Perhaps future discoveries will reveal that time is even weirder than relativity suggests. Perhaps there are conditions inside black holes during the Big Bang at quantum scales where time behaves in ways Einstein never imagined. Perhaps time itself is not fundamental. Perhaps it emerges from some deeper quantum structure, the way temperature emerges from the motion of molecules. Or perhaps relativity's description of time is essentially correct, and quantum gravity will confirm and extend it rather than overthrowing it. We're on the frontier of understanding. We know so much more than we did a century ago, but the universe still holds mysteries, and that's exciting, because it means there's more to discover, more surprises waiting, more profound truths about reality yet to be revealed. But here's what we do know with certainty. Time is not absolute. Time dilates with velocity and gravity. You can manipulate time by changing your speed and position in gravitational fields. These aren't speculations. These are established facts, and they're extraordinary. So here we are, at the end of our journey through time dilation. We started with Interstellar's Miller's planet, 1 hour equaling 7 years, and discovered that this seemingly impossible scenario is grounded in real physics. We learned that Newton's absolute time was wrong, that Einstein revolutionized our understanding with special and general relativity. That time is woven together with space into four-dimensional spacetime. We explored velocity-based time dilation. The faster you move, the slower your time ticks from another observer's perspective. We explored gravitational time dilation. The stronger the gravity, the slower time flows. We saw that your head ages faster than your feet by nanoseconds over a lifetime. That atomic clocks on mountains tick faster than clocks in valleys. We learned about the Haffel-Keating experiment, where clocks flown on airplanes gained and lost time exactly as Einstein predicted. We discovered that GPS satellites require precise relativistic corrections, 38 microseconds per day, or the system would be useless within hours. We found that astronauts aboard the ISS age milliseconds slower than people on Earth. That Scott Kelly traveled 10 milliseconds into his twin brother's future. That Sergei Krikalev is humanity's greatest time traveler, 20 milliseconds younger than he should be. We witnessed nature's demonstration of time dilation in cosmic ray muons that reach Earth's surface only because relativistic speeds stretch their lifespans. We explored particle accelerators where time dilation factors reach thousands, where unstable particles live dramatically longer than they would at rest. We journeyed to black holes, where time dilation becomes extreme, where time can slow to a crawl near the event horizon, where Gargantua's immense mass and rapid spin could create the conditions for Miller's planet's time dilation. we contemplated the implications for interstellar travel, how crews traveling at relativistic speeds would age years while decades or centuries pass on Earth, becoming temporally displaced from their own civilization. And we reflected on the philosophical meaning of all this, that time is not universal, that there is no absolute now, that the universe is far stranger than our intuitions suggest. But here's the most important thing I want you to take away from this. Time dilation is real. Right now, at this very moment, time is flowing at different rates for different parts of the universe. GPS satellites are ticking faster. Astronauts are aging slower. Months are living longer. Your head is aging faster than your feet. You're not moving through time at some universal, absolute rate. You're moving through time at a rate determined by your velocity and your position in gravitational fields. You're traveling through space-time on a path that's uniquely yours, and that path determines how much time you experience. Every step you take, every movement you make, every change in altitude or velocity, however tiny, affects the flow of your time. You are, in a very real sense, a time traveler. You always have been. Most of the time, the effects are so microscopically small that they don't matter. Your everyday experience of time is essentially Newtonian. Time seems absolute and universal, but zoom out. Look at the bigger picture. Consider astronauts, GPS satellites, cosmic particles, black holes. Time is flexible. Time can be manipulated. The universe allows you to experience less time than others by moving fast or descending into gravitational wells. This is our reality, not science fiction, not speculation. Established, tested, confirmed physics. Einstein figured it out over a century ago, and we've been verifying it ever since. The universe is stranger, more beautiful, and more intricate than our ancestors ever imagined. And we, humanity, have figured out some of its deepest secrets. We've learned that time itself is not fixed, that time bends and stretches, that gravity can slow time, that speed can slow time, that you can travel to the future. This knowledge is yours now. This understanding of how reality actually works beneath the surface of everyday experience. Time is relative. And that truth, that profound insight into the nature of existence, is one of humanity's greatest achievements. So the next time you check a clock, remember, that clock is not measuring some absolute universal time. It's measuring the accumulated proper time along the clock's path through space-time. Different clocks, traveling different paths, accumulate different amounts of time. Your time is yours, shaped by your velocity, shaped by your position in Earth's gravitational field, shaped by your journey through the four-dimensional fabric of space-time. You are not a passive passenger through time. You are actively traversing space-time, accumulating proper time along your world line. And if you ever doubted that the universe is extraordinary, if you ever wondered whether reality is as amazing as fiction portrays it, remember time dilation. Remember that physics is real, that Einstein was right, that time bends. The universe is far more wonderful than we knew. And understanding that wonder, truly grasping the flexible nature of time, is one of the most profound gifts science can offer. Take a moment. Really think about it. Time is not what you thought it was, and that's beautiful.